On this video, we're going to learn about what's called implicit differentiation. So I have here an equation of a circle, x squared plus y squared equals 25, and we've graphed that there so you can see it. And so what we have is this x squared plus y squared equals 25, the way it's written would be considered an implicit function. That is, y we assume is a function of x, even though we haven't separated it off and written it as y equals f of x, where y is by itself. Now, in this case, we can solve for y. It turns out then that it's actually two different functions, because if we subtract the x squared to the other side, we're going to get actually a positive and a negative square root of 25 minus x squared. So the positive square root is that top half of the circle, that semicircle there. And the negative square root of 25 minus x squared is the bottom half, the bottom semicircle. So what I'm going to do is we're going to find the derivative here at the point at x equals, so we're going to find the derivative at x equals 3. And then I'm going to work through it here using kind of our old methods that we know, and then I'm going to come back and do it using this other idea of implicit differentiation, just to show you that we do in fact get the same thing. So then hopefully you can trust it, so that when we can't separate the y out like we could in this case, we can still use this technique of implicit differentiation to find the derivative. So in the first case, so let's take first the y equals the positive square root of 25 minus x squared. So I'm going to write it in a more derivative-friendly form. And so we'll get that the derivative is going to be using our chain rule, 1/2 times 25 minus x squared to the negative 1/2, and then times the derivative of the inside function, that negative 2x. So we can see that 2 and the 1/2 and the negative 2x are going to cancel each other out. So we're going to get, I think, a negative x over the square root of 25 minus x squared. I'm just going to call that y prime. And so then if we evaluate that at x equals 3, we're going to get 3 squared is 9, 25 minus 9 is 16. And the square root of 16 is 4, so we're going to get a negative 3/4. So that's one of our derivatives. Now I'm going to come back and do the other one, the negative square root of 25 minus x squared. So in a similar fashion, I'm going to rewrite that as to the 1/2 power. Again, doing our chain rule, we're going to bring the 1/2 down, subtract 1 from the exponent, and multiply by the derivative of the inside function. Once again, the 1/2 and the negative 2 are going to cancel. And this time, though, we have two negatives, so it'll be x over the square root of 25 minus x squared. So when we evaluate this one at 3, we're going to get a positive 3/4. So you can see we get the one derivative is negative 3/4, one is going to be positive 3/4. Now here's the idea for implicit differentiation. We're going to look at this function defined implicitly, where we haven't separated the y off by itself. We're going to differentiate this, but we're going to treat y like a function of x. So that means when we go to differentiate y squared, we're going to have to treat that as if it is a chain rule derivative, like it's going to be some unknown f of x to the second. So let's see what that's going to look like. The derivative of x squared is still 2x. Now we're going to go 2 times y to the first. Now the derivative of that inside function, so this would be like 2 times f of x to the first, and then we would say times the derivative of the inside function. Well, we're going to call that inside function, instead of calling it f prime, we're just going to call it y prime. So I don't want to really use that to the first, that's too confusing. I'm going to call that y prime. So there's our chain rule as applied to the function y to the second. It's 2 times y to the first times the derivative of y, which we're just going to call y prime. Now what we're going to do is get the y prime by itself. So to do that, we're going to subtract the 2x to the other side, and then we're going to divide by the 2y, and so that's going to look like negative x over y. So here is our derivative, y prime equals negative x over y. So we can see that when we go to evaluate this at x equals 3, that we need a y value as well. So we're going to have to come back now. If I can bring my pen back. So we're going to come back to here, and if we plug in 3 squared is 9, plus y squared is 25. So y squared is going to equal 16. So you can see we'll get two different values for y depending on when we plug in x equals 3, because since we have really two functions, there's going to be a 3 comma 4 here, and there's also going to be a 3 comma negative 4 that both have that x value of 3. So if we plug in the 3 and the 4, then that's going to give us a negative 3/4, which matches the derivative we got right there. And if we plug in the 3 comma negative 4, then our y prime is going to be, the negative x will be a negative 3 over negative 4, which is a positive 3/4, which matches the derivative we got there. The point being that this idea of implicit differentiation really does work. It's consistent with what we did using our old method. So hopefully now we can trust it when problems where there's no way we could separate it off. So I'm going to work a few examples here. I'm going to take x squared minus xy plus y squared is equal to 3. And then we're going to ask a series of questions here. First, can we find y prime? Secondly, can we find an equation of the tangent line to that curve of the tangent line? And I'm going to tell you at the point 1 comma negative 1. Then I'm going to ask you to find y double prime also at that same point 1 negative 1. Okay? Let's see what we got here. So first, here's our chance to do implicit differentiation. So the derivative of x squared is 2x. Now this is a tricky one. This is a product rule. So you can do, I think what people seem to have the most success with is if they say it's a minus, and then we have the first x times the derivative of the second y prime plus the second y times the derivative of the first, which is 1. And then the derivative of y squared is going to be 2y to the first times the derivative of y, which is y prime, and the derivative of a constant is 0. So we can distribute this negative sign, xy prime minus y plus 2y y prime equals 0. We're going to keep the y prime terms on one side and move the non-y prime terms to the other side. So I'm going to leave on the left side the 2y y prime and the minus xy prime. On the other side, I'm going to move over the 2x and also add that y. So I think I'll call that, just to make it more appealing, more aesthetically pleasing, y minus 2x, but that's just window dressing. Now we can factor out the y prime, leaving behind 2y minus x, and we still have our y minus 2x on the other side. So finally, solving for y prime, we will divide all of that other stuff, the 2y minus x, to the other side, and this is our expression for y prime, the derivative. So now, to answer the question part B, to find an equation of a tangent line, we need a point, which we have, and we need the slope, which is going to come from here when we plug in 1 for x and negative 1 for y. So that's going to look like negative 1 minus 2 times 1 over 2 times negative 1 minus 1. So that's going to be a negative 1 minus 2 is going to be a negative 3, and a negative 2 minus 1 is also negative 3, which means our slope is going to be equal to 1. So there's our slope. Here's our point. So our equation of a line is going to be y plus 1 equals 1 times x minus 1. We can hardly resist there. We might as well go ahead and put it into slope-intercept form, but either one of those would be just fine. So there's our tangent line. Now, we're going to find the second derivative and then evaluate that at the point 1, negative 1. So we're going to take our first derivative now, and we're going to differentiate that. So I'll do the left side. There's y double prime. Now on the right side, we're going to have to do a quotient rule. So we're going to get the denominator, 2y minus x, times the derivative of the numerator, which is y prime minus 2, minus the numerator, y minus 2x, times the derivative of the denominator, which is going to be 2y prime minus 1, all over the denominator squared. Now, in general, if all I wanted was the value at 1, negative 1, I would plug in the numbers right now. Well, let's go ahead and do that. So we're going to evaluate this now. But let's see, we have these y primes in there. So we're going to need to come back to our y prime expression here, and let's plug that in. Oh, we did already. We found that it was equal to 1. So our y prime evaluated at x equals 1 and y equals negative 1 is equal to 1. So what we're going to get now then is going to be 2 times negative 1 minus the 1. I'm plugging in 1 for x and negative 1 for y, and I'm going to plug in 1 where we see the y prime. So that's going to be 1 minus 2 there, minus the y is negative 1, minus 2 times 1 is a minus 2, 2 times y prime, which is 1, minus 1, all over 2 times y, which is going to be a negative 2, minus 1, and we're going to square that. You with me? So we're going to get 2 times negative 1 is negative 2 minus 1 is negative 3. 1 minus negative 2 is negative 1. Minus, we got a negative 3 times 1. And in the bottom, we got negative 3 squared is 9. So I think that's 3 minus a negative 3 over 9 is going to be 6/9, which is 2/3. It doesn't always work out that nice, I'll tell you that. Now, I want to move to the next panel, and let's talk about some more challenging ones. So we're going to see how I'm going to jump. This is a whole nother level here. E to the xy is equal to the natural log of x plus y minus 2xy. We're going to try to find y prime here. So this has some complications here. So I want to make sure we know how to do this. Remember, the derivative of e to the u is going to be e to the u du. So this is going to be the same exponential back, e to the xy, times the derivative of x times y is a product rule derivative. So we have the first x times the derivative of the second, plus the second y times the derivative of x, which is 1. On the other side, remember, we're going to get du over u. So we're going to get the 1 over u, there's our denominator, and then in the numerator, the derivative of x plus y is 1 plus y prime. Now, this is our complicated product rule here, so I'm going to go minus the first 2x times the derivative of the second, plus the second times the derivative of the first. Now, we have a bunch of terms with y prime and also a bunch that do not have y prime. So we're going to need to distribute here to separate out the y prime from the y terms. So that's going to be xy prime times e to the xy plus y times e to the xy. Now on the other side, we also need to separate these off because one doesn't have a y prime and the other one does, and they're going to need to go on different sides of the equal sign. And then we can distribute our negative sign to get here. Now we're making progress. So we're going to move that y primes. I'm going to just take them all to the left side. So we have xy prime e to the xy. I'm going to subtract the y prime over x plus y and add the 2xy prime all to the left side. Then we have that 1 over x plus y, the minus 2y, and I'm going to subtract that y e to the xy that doesn't have a y prime in it to the right side. Okay, we're getting there. Now the left side has all the y prime terms. I'm going to factor those out. That's going to leave behind x e to the xy minus 1 over x plus y plus 2x. On the other side, that's just going to stay as it is. There's not really much of anything more we want to do with that. Now I'm going to divide all of this stuff, this multiplying y prime, to the other side. I do not expect you to do any kind of simplification here. This is just an exercise to see what in the world you do with all of these exponentials and logarithms and product rules and so on. So if we can get to this point right here, I will be thrilled, because that's a pretty complicated implicit differentiation problem. Very good.